Okay, so in the previous video, we came up with this idea of a growth function, and we showed that if you could come up with a growth function for your hypothesis class, then you could come up with a new kind of form of a bound on the generalization error. But this is a little bit unsatisfactory for a couple of reasons. For one, the growth function is different for different values of m. And then also it was kind of a bit of a pain to compute. So now I'm going to introduce kind of something that is a little bit more satisfying. And that's what's called the VC dimension of a hypothesis class. So it's defined in this very mathy way as the VC dimension of H is the max over the m's such that the growth function of m is equal to 2 to the m. Okay, what does that mean? That means that the VC dimension is the largest possible m, so the largest possible of number of points, such that the hypothesis class can accurately classify every possible dichotomy on those points. Okay, so you could think about how if you have 3 points for some hypothesis class, it might be possible to classify all 8 of those combinations. But if you move to 4 points, it might not be possible with your hypothesis class to get every possible dichotomy on those 4 points. Okay, and so in that case, we would say that a VC dimension is 3. Okay? So this idea was invented by Vapnik and Chervenenkis in the early 60s. That's what the V and the C comes from. And then it was continually kind of updated in the context of learning theory for the next 30 some years. So I want to define this in an alternate way just so that we can bring in some very common terminology that's used in the learning theory literature, and that is the idea of a set of points being shattered by a hypothesis class. So we say a set of points S is shattered by hypothesis class H if H can correctly classify all possible labelings of the points in S. Okay, and so then we can redefine the VC dimension as the max over the size of S such that H shatters S. And then just kind of a subtlety of this is that for this to be the VC dimension, we only have to find some S, some configuration of the points. So let's say that the size of S is 3. If I could find a spatial configuration like this that H can shatter, then I'm kind of done. And there could be some kind of pathological cases where the set can't be shattered, like in some examples, if the points are collinear like this, then they can't be shattered, but that doesn't matter for VC dimension. All I need to do is find some configuration of m number of points that can be shattered by the hypothesis class. And so now proving these things is a little bit tricky. You need to prove a lower bound on the number of points that can be shattered. And usually this is not so bad. It's done by just coming up with a configuration that's convenient and then just demonstrating that you can do the shattering. The hard part is finding the upper bound. So you want to find, the smallest number of, or the largest number of points that it works, and then you need to find the smallest number of points where it doesn't work. And in that case, for the upper bound, you need to show kind of that m points cannot be shattered given any possible configuration. And that's harder because you can't kind of exhaustively come up with examples to show that a set of points can't be shattered. So you have to use kind of a rigorous mathematical argument, and I'm going to do that one time in this video, and then the rest of the time I'm going to kind of just wave my hands with it. Okay, so let's do an example. So let's say we want to find the VC dimension for intervals on the real line. So again, this is the Frank the Alien case. And the interval hypothesis is defined in the usual way. And so first of all, just my gut instinct is that I can probably shatter 2 points. And so I'm going to run through those 2 to the 2, which is 4 possible dichotomies, and show that I can do it. And then we'll talk about how to find an upper bound. Okay, so the 4 possible combinations kind of look like this. So you could have 2 points and both of them are positive, and then you just slap an interval around it like so. And then you could have a case where the first one is positive and the second is negative, and then you throw an interval around the first one. If the second one is positive and the first is negative, you throw an interval around the second one. And finally, if both of the points are negative, you throw an interval kind of on the outside, and then you're done. So this was taking all 4 possible combinations of 2 points, combinations of labelings, and we showed that with intervals, I can accurately classify all 4 combinations, and that means that we've shattered this set of 2 points. Okay, so from this we know that the VC dimension for intervals is at least 2. It might be bigger. But now we need to try to prove an upper bound. So what I'd like to do is I'd like to be able to prove that there is no set of 3 points that can be shattered. Okay? And so here, this is just kind of a hand-wavy example. Here I've thrown down a specific, kind of arbitrary-ish example. And I've come up with a labeling that I know doesn't work. Because if it goes positive, negative, positive, then, there's no way that I can accurately capture this with an interval. If I try to throw an interval around here, then I misclassify this point. If I try to throw an interval around here, I misclassify this point. If I try to throw an interval around the whole thing, then I misclassify the point in the middle. Okay, so this is one where it's impossible to shatter. So it must be the case that the VC dimension is less than 3, and so together with the lower bound and upper bound, I can conclude that the VC dimension for intervals on the real line is 2. Okay, so let's look at how you could actually prove this upper bound kind of in a more rigorous way, where we show that the set can't possibly be shattered for any possible geometric configuration of S. So we want to do this for the interval case where the size of S is 3, so there's 3 points. And I'm going to do this as follows. So I'm going to say let x1, x2, x3 be arbitrary points, and I'm going to, without loss of generality, kind of apply an ordering to them. So x1 is less than or equal to x2 is less than or equal to x3. And notice this equal means they sort of could be sitting right on top of each other. And so I'm going to consider the case from the previous example that I showed in the picture, where I consider the labeling +1, -1, +1. And assume that I've got some, h, which is the interval from a to b that I think works, and now I'm going to show that it doesn't really work. So since y1 is +1, that's this one, it must be the case that in order for x1 to be in that interval, it must be the case that a is less than or equal to x1. And similarly, because y3 is +1, it must be the case that b is greater than or equal to x3, because x3 better be on the left side of b. And just from the assumed ordering I had from the points, that means that a is less than or equal to x1, which is less than or equal to x2, which is less than or equal to x3, which is less than or equal to b. But that doesn't work, because according to our hypothesis, that means that we should classify x2 as positive as well, but according to the label, x2 should be negative. And so that's a contradiction, and so we've proved that there's no possible way that we could get a shattering of 3 points. Okay, and so this is all these arguments for these upper bounds tend to be kind of geometric or linear algebraic, at least, kind of like this. Okay, so now we have a kind of a rough idea of what the VC dimension is. Let's see what this does for our generalization bound. So same kind of premises. H is a hypothesis class. Let's call the VC dimension D, just so that it will fit on the slide when I put it in formulas. Then for any fixed delta greater than 0, with probability at least 1 minus delta, we have the following bound. So the complexity term now, this one is exactly the same as it was. And now the complexity term that depends on the complexity of H looks like this. It's 2 times D, remember D is the VC dimension, of the natural log of EM divided by D, all divided by M. And this E is exactly what you think it is. It's like E to the 1, right? And so, okay, so here's our new bound. And if you think about this, this is a little bit nice. So let's say that we fix delta and pick M to be bigger than N, and then let M and D kind of grow. Then you can show that eventually this complexity term kind of will dwarf this one. And then the generalization bound looks like the generalization error is bounded by the training error plus so big O of the square root of natural log of M over D divided by M over D. So I just rearranged this and assumed that the E goes into this constant out in front. And so if you look at this, this says that the training error is a good indication of the classification error if M is much, much bigger than D, right? Because as these things get bigger, the natural log is going to grow fairly slowly, and it's going to grow in particular much slowly than this linear function of M over D. So eventually this is going to kind of go towards 0. Okay? And that's just a nice kind of simpler way of looking at it. Okay, so here let's look at another example. So let's say that X are all two-dimensional points, and I want to find the VC dimension of H, where H is the class of all minimal axis-aligned rectangles, where here I'm defining the hypothesis such that, you know, if points are inside of the rectangle, then they're positive, and if they're outside of the rectangle, then they're negative. And so I want to show that we can shatter some set of m equals 4 points. So remember, we don't have to show we can shatter every set. We just have to find a convenient set that works and demonstrate that we can do it. And so I'm going to do a couple of these, and then you should maybe kind of try to show the rest on your own, because how many possible dichotomies are there? There's 4 points, so there's 2 to the 4, which is 16 dichotomies. And so here's one example where these ones up here are positive and this is negative, and I can classify this by throwing a rectangle like this around it. Okay, and then here's another example where now I've got these two are positive and these two are negative, and of course it's pretty easy to see that I could throw a rectangle around this like so, and that would accurately classify this set of labels. Okay, so you know, there's 2 out of the 16, but I think you can go through and try to do the rest yourself and see that it is possible to accurately classify all of the 16 possible dichotomies. Okay, so what about if we try to go bigger? If we have 5 points, and I'm going to do this kind of a hand-wavy way. I'm going to show kind of an arbitrary-ish or a reasonable, non-seemingly pathological configuration and show that I can't do this with 5 points. Okay? And so, you know, this case, for this configuration where I've got this labeling where I've got kind of a set of positive points, and then I've got a negative point that's kind of inside the convex hole of the positive points, then this is pretty easy to say that there's kind of no way that I can get, you know, all 4 of the red points in the box without getting the blue point in the box. Okay, and so in practice, you would have to prove this kind of in a more mathematically rigorous way, but for this is just kind of to give you a flavor for it. So what does that mean? That means that we can't do 5, but we could do 4, so that means the VC dimension of the set of axis-aligned rectangles is 4. Okay, another example. Let's say that X is again the set of 2D points, and you want to find the VC dimension of H, where H is the set of all linear classifiers. So this is something like logistic regression or SVM with a linear kernel. And so here, let's see if we can shatter sets of 3 points, and because there's only 3, there's only 8 possible dichotomies, and so I can show them all to you on the screen. So what I want to do is I want to come through with kind of linear decision boundaries, and I want to show that I can kind of accurately classify all these. So here would be one that would accurately classify this, where the stuff on the kind of left side of the line is positive. Here I could do something like this, and so on and so forth, and you could go through all of these cases and get something like this. And this shows that this particular set of 3 points can be shattered by the class of linear classifiers. On the other hand, you can't shatter a set of 4 points, so if you consider an example like this, there's no way to get this one, because here, if I draw my decision boundary here, then I get the reds right, but I misclassify this blue point. If I try to do it over here, then I get the reds right, but I misclassify this blue point. Okay. Again, this is not a rigorous proof. You would have to do something more mathematical to do this, but just to give you some kind of intuition about this. So it looks like in this case, the set of linear classifiers have VC dimension 3. Okay, so in fact, you know, so this was just in 2 dimensions. If you went up to 3 dimensions, then you'd have, you know, a linear classifier would give you hyperplanes. And then you can ask the same kind of questions. And so, in fact, and you can prove this, that if your training examples are in Rn, so they're vectors of length n, you can show that a linear classifier will have VC dimension of n plus 1. Okay, so let's think about what this means for this generalization bound. And so this is kind of the exact same bound that I wrote up before, but this seems kind of good. All of the examples that we've looked at so far, the VC dimension has been relatively small. This value of D is relatively small, and that means that, you know, we don't have to make M too large to drive that complexity term down. But, you know, maybe some of the examples that we've looked at in the class are not quite this nice. So you could think about what's the VC dimension of k nearest neighbors with k equals 1. And if you think about this, it's pretty easy to see that the VC dimension of k nearest neighbors with k equals 1 is infinity, right? Because if you're doing k nearest neighbors, where the nearest neighbors number of nearest neighbors you consider is just 1, then effectively what you're doing is you're going around and you're putting a little circular decision boundary around the positive points, and everything outside of that is a negative point. And obviously, with something as flexible as that, you could shatter some set for any number of points, right? As long as none of the points lie right on top of each other, you can really easily do this. And so because you can do this for an arbitrary number of points, that means the VC dimension is infinity. Okay, so just to kind of summarize, the VC dimension is a convenient measure of the complexity of infinite hypotheses classes. And once we have that convenient measure, then we can insert it into our generalization bounds, and we can actually be able to say things about the relationship between the training error of a hypothesis and the generalization error and the complexity of the model. Okay? And so in class, we will answer any of your questions, and we'll work through some simple examples. And in particular, we'll look at examples of kind of more rigorous proofs of VC dimension and talk about what I expect you to be able to do. And so looking forward, we're going to look at a particular type of classifier that seems to kind of defy the pessimistic generalization bounds that we get based on the complexity of infinite dimensional hypotheses classes. And those, in particular, those kind of class of models are what are called margin maximizing models. And in particular, a specific flavor of these margin maximizing classifiers are things that are called support vector machines. And we're going to spend a significant amount of time talking about support vector machines. And at the end, we'll kind of talk about how you get, in the case of support vector machines, you get these really, really nice generalization bounds that give you kind of way better results than you normally would expect.